Almost all of scatter radiation that we encounter in diagnostic radiology come from Compton scattering. An incident photon with relatively high energy strikes a free outer shell electrons, ejecting it from its orbit. That is, incident photon with relatively high energy strikes a free outer shell electrons and ejecting it from its orbit. The photon is deflected by electron so that it travels in new direction as a scattered photon. The photon always retains parts of its original energy. The reaction produces an ion pair, a positive ion, a negative electron, and a scattered photon. This ejected electron is also called recoil electron. What is the application of Compton scattering in diagnostic radiology? In diagnostic energy range up to 150 keV, photon retain most of its original energy and very little is transferred to recoil electrons. At narrow angle of deflection, scattered photon retains most of its initial energy, and this is a problem in diagnostic energy because these scattered photons have an excellent chance of reaching an X-ray film and produce fog. They cannot be removed by filters because they are too energetic, and they cannot be removed by grid because their angle of deflection is too small. So very high ratio grid is used, which ultimately increases the passing radiation dose. Scattered radiation from Compton scattering is also a major safety hazard because even if scattered photon has been deflected by 90 degrees, it still retains most of its initial energy and is hazardous for fluoroscopists and other personnel in the exposure room. Greater the angle of scatter, lower the residual deflected photon energy and higher the subsequent electron energy. The electron is ejected and deflected. This is the angle of deflection, that is the scattering of photon. Probability of Compton scattering depends on the energy of the radiation and density of the observer. It increases with lower diagnostic energy, that is, it decreases with increase in energy. Increases with outer shell electron, that is electron density, and it increases with physical density of the material, and it does not depend on atomic number. While photoelectric absorption depends on atomic number, this does not depend on atomic number. That is, scattered radiation can be similar in both bone and soft tissue.